Hi everyone, this is the Applied Statistics in Healthcare series, and in this series we're covering logistic regression. So we'll begin with purposes in learning regression, and they are first to help make better decisions faster with an all-in-one approach. Oftentimes we're trying to figure out if certain things like age, gender, and diagnosis have an impact on the outcome. And one way that we can look at all of those, all three at the same time, to give us an accurate understanding of the effective age while controlling for gender and diagnosis, is to do it with a logistic regression. And so that leads us to number 2, which is to increase accuracy by controlling for other competing causes, such as getting the effective age while controlling for gender and the primary diagnosis. Another purpose is to save resources. We can make better use of the data we already have, and we can do that with advanced methods that work well on small samples like aggregated data. Number 4, to develop an expertise in identifying trends. Knowing a regression trend line allows us to better interpret a standard report's results. For example, if we have something that has a 45-degree angle, then that's probably a significant result. Number 5, learn how to risk adjust and do predictive modeling. The same regression can allow you to do both, and also if we want to do hypothesis testing. The intent or the purpose of doing the regression may determine that we're doing risk adjustment or predictive modeling, but it's the same process. So we do have some extra things to consider, but it's the same regression. So we can learn how to do all these different things in one process. Number 6, learn concepts that are the foundation of all other regression types. If you've covered multiple linear regression, you've probably already reviewed some of these concepts, but once you learn these concepts in one type of regression, these are things that you can apply to different types of regressions or different phenomena that you're going to cover. Number 7, identify group trends useful in telling us if medical centers are improving, getting worse, and all on the path to reaching our goals. So we can explore trends, and we can look at bigger questions and try to predict where we're going to be at in the future. So questions that we can answer with logistic regression, just to give us an idea of why we would want to learn logistic regression. Here's some questions that we can answer with logistic regression. For example, is smoking linked to lung cancer? And from our logistic regression, we may find out that yes, smokers have significantly higher levels of lung cancer. Another question is, do older passengers have lower chances of surviving the Titanic? And we might actually be able to answer that as yes, and we can also say that for every 1 year older, passengers have about a 1% less chance of survival. Another question that we can ask is, are men more likely to die 30 days after a heart attack? And from some studies, we might find out that men are twice as likely to die than women. And we can even take into consideration multiple factors. The first 3 questions, we're just looking at one factor compared with an outcome, but we can look at multiple factors and answer questions such as, are men more likely to die 30 days after a heart attack, controlling for age? And then we may find out that men are 1.5 times as more likely to die than women after making all things equal on age. In each question, we have an outcome with 2 options. For example, readmissions or not, alive or dead. And we have a factor that we want to know if different levels lead us to increase the chances for the outcome. And we'll start with session 1. that's the introduction to logistic regression. We're going to look at background, and we're going to look at the example of smoking and lung cancer. And here's our syllabus. There will be 4 sessions. We're going to cover 4 different topics. The first would be Introduction to Logistic Regression, and that starts on slide 4. And in the background, we'll look at things such as logits, odds ratio, and probabilities. These are the foundation of this type of analysis. We'll also look at the hypothesis testing example, and that's the 1951 Dahl and Hill study on lung cancer and smoking. And in it, we're using aggregated data. We'll also do an example using aggregated data. For session 2, we're going to do diagnostic or explanatory models. Some of the topics are missing data, nonlinearity, and interactions, and that starts on slide 57. And our first case study is on major coronary disease. For session 3, we're going to do prognostic or predictive models. We'll focus on data reduction and validation. We'll also look at observed expected ratios and excess death, and that begins on slide 73. In our second case study, we'll look at 30-day mortality after an acute myocardial infarction, in other words, a heart attack. For session 4, we'll do another prognostic model. We'll cover the topics of implementing a model, selecting thresholds, and decision analysis, and that begins on slide 93. And for our third case study, we're going to look at 30-day diabetes readmissions. In this course, we'll have R and SAS files. We're going to have those files that will cover what we're going to review, or most of the tables and graphs that we're going to look at. We're going to have through R and SAS. I'm actually able to do a little more with R because I'm using the RMS package. So we'll have more things in R that we can look at, but we'll have code for both and data for both. And if you'd like to use my Shiny app, which everything in this, all the tables and graphs come out of, then you can find it in my GitHub site. And on the right, just to give you an idea of the Shiny app, it's a graphic user interface. So a lot of drop-down boxes and yes/no options or boxes as well. And so that's what kind of what it looks like on the far right at the bottom. Okay, so these are some of the topics we're going to cover. Interpretation of results, variable importance, partial predictions, validations, which covers calibration and discrimination, nomograms, working with predictions, contrast, nonlinearity, interactions, excess deaths, observed expected ratios, hypothesis, test effect size, and predictive modeling. We'll use 5 data files. The first one is DHLC, and that's the Dahl and Hill lung cancer study. The second file is a CATH2, and that's significant coronary disease. Then we have data for the 30-day death after a heart attack, data for the 30-day readmission for diabetes patients, and that last file is for hypertension. And just to give us an idea of what the definition of multiple logistic regression is, we'll look at what each part of that name comes from. So regression, we're regressing the outcome on one or more predictors, and that's either a simple or a multiple regression. Linear, I'll use the term linear a few times throughout the course, and that can refer to a trend line that best represents the relationship between the outcome and the predictor, or it could also be the additive nature of regression models. For example, y equals x1 plus x2 instead of y equals x1 multiplied by x2. We'll have outcomes, and in a logistic regression, the outcomes are 0 and 1. In ordinary least squares, or what we often refer to as multiple linear regression, the outcome has many more values, and they range from 0 to an infinite number, and they actually can include negative numbers as well, but for logistic regression, we're confined to values that range from our expected values that range from 0 to 1. And our outcomes are 0 and 1, but when we return our output, it comes out as a probability between 0 and 1. And logistic regression is analogous to what is commonly referred to as linear regression, but for two categories. And we call those binary outcomes. We'll draw on comparisons between the two and use the OLS notes and videos to provide more detail on our concepts. If you're familiar with multiple linear regression, logistic regression is essentially the same idea. The rules are identical on the right hand of the equal sign. We have special considerations on the left side of the equal sign. For example, readmissions equals age plus gender plus diagnosis. We'll cover statistical concepts, and I have links to the Intro to Statistics videos. We have them from week 3 and week 4, and these are the YouTube links, and I have the minutes that these different topics begin in, and also where they end at. So if throughout the notes you'll notice that in some slides we have these purple click this link boxes, and that allows you to once you do click on it, you can come back to find the time and YouTube link to our past courses. So keep an eye out for these purple links if there's something you'd like to learn more about. And we also have it from the multiple linear regression sessions for week 2, 3, and 5. We have these different topics covered at these different time points, and you have the YouTube links in each of these slides. We have 3 reasons for doing regressions. They are hypothesis testing. For example, we expect the group that received the intervention will have a lower readmission rate. We can also do regression to get the effect size estimation. We may want to know how much of an effect has on an outcome. For example, what percentage of readmissions is reduced by an intervention? What are the cost savings from an intervention group, and so on. And the third reason is predictive modeling. We can create predicted scores for individuals to assign care. For example, we may try to predict a patient or a group chance of survival, length of stay, a child's lung capacity, etc. So we may use, of these 3 reasons, we may do an analysis for one or multiple reasons, or actually for all 3 reasons. But a single regression allows us to do all 3 simultaneously if we would like. And this may lead to the question, what is logistic regression? Logistic regression is a method for estimating coefficients or parameters that describe the relationship between independent variables and dependent variables, or outcomes, another way to say it. Rather than assuming all patients have a greater chance of readmission, we can test if there is a difference based on age. So if we think age is important, we can see what the effect of age is on whatever outcome we're looking at. Logistic regression is similar to linear regression. How it differs is that logistic regression is a probability model. Because probabilities can be converted into odds, we also get odds ratios in our results. We develop a conceptual model. For example, it may look like this. A hospital readmission is equal to, or the probability of a hospital readmission is equal to a patient's age, their sex, and their primary diagnosis. Some variables may increase our chances while others decrease it. In some things I've seen age increase chances of readmission, but for other things it may actually decrease it. But this gives us once we enter our different factors into a formula that predicts the probability of readmission, then it gives us an idea of what the direction of that relationship between our factors on the right side and our outcome on the left side. And one way that we usually begin by looking at outcomes that are just have two categories, which is why we use logistic regression, is we begin with the 2x2 contingency table. And that just gives us a good way of summarizing our results in these 2x2 tables. For example, we may want to know if pneumonia, which is an exposure in this table on the left side, if we want to know if pneumonia patients have a higher chance of readmissions, and that would be the columns in this table. And for this data, our data for these different cells, A, B, C, and D, would be 20, 30, 5, and 45. So from this, we can see that there are more readmissions for pneumonia patients. It would be 20 in the top left cell versus 5 in the bottom left cell. So from that, we can see that more pneumonia patients have readmissions than non-pneumonia patients. We can work with probabilities from binary outcomes. One way that we do it is through the risk difference and risk ratios. For example, on the right side, P1, the probability for group 1 might be 0.0026, and the probability for group 2 would be 0.007. Then we can calculate the risk difference, which is just P1 minus P2. 0.0026 minus 0.007 equals 0.0019. Or we can do a risk ratio, which is just those two numbers, one divided by the other, and that gives us a risk ratio of 3.7. These are commonly used statistics, but we use odds ratios because of their more flexible statistical qualities. And so we're starting here as one possibility of how to use these, how to use probabilities, but as we're going to see in this next slide, there are limitations to what we can do with risk ratios or risk differences. A better way to work with probabilities is with the odds ratio. And the odds ratio allows us to compare odds that are in favor of success versus odds that are not. We can convert probabilities into odds. So we're still working with probabilities, but now we're converting them into odds. For example, something has the probability of 0.80. The inverse would be that the probability is 0.20. So if we divide 0.8 divided by 1 minus 0.8 or 0.2, we know that there's an odds that the odds in favor of something is 4 times that of not. So 4 to 1 odds means of 5 people, 4 would have an outcome of yes versus that one person that had an outcome of no. So these are just so odds ratios gives us something that we can do more with our analysis than if we just look at probabilities alone. Odds ratios are calculated from probabilities, but they don't have the limitations that we have with strictly working with just the risk difference or a risk ratio. And there are various odds ratio calculations for the exposure or our factor. And what we're most interested in is going back to those questions. We may want to know if pneumonia patients are more likely to have readmissions than not. So what we really want to know is what the effect is of whatever factor we're considering, what that effect is on the outcome. And so because of that that mathematical relationships between proportions and odds ratios, it turns out there's actually more than one way to calculate a proportion or an odds ratio. And this slide emphasizes that proportions or probabilities and whole numbers are related. They both give us odds ratios. So for this example, we may want to know, do pneumonia patients have a greater chance of readmissions compared to non-pneumonia patients? So what we can do is we can divide 20 by 30, and we can compare that with 5 divided by 45. So in example 2 on the whole numbers, our odds ratios are 20 divided by 30 and that value divided by 5 divided by 45. And from this we see that pneumonia patients are about 6 times more likely to have a readmission than non-pneumonia patients. So that's what an odds ratio is. It tells us what are the odds of one group versus the odds of another group. And if we believe that pneumonia patients, for example, if we expect pneumonia patients to have higher chances for pneumonia, then we expect that the odds ratio of 20 divided by 30 and 5 divided by 45 to be greater than 1, which it is. It's about 6. And here's an example of on passive smoking, and that's what we more often refer to as secondhand smoke and lung cancer. So in this example, the odds ratio of passive smokers with lung cancer to passive smokers without lung cancer is 2 to 1. Passive smokers are twice as likely to have lung cancer. And on this table on the left side, these are the passive smokers do not smoke at all. So they are in a household where either their spouse or another relative smokes, and they're getting exposed to secondhand smoke. And so one way that we can calculate the odds, we would first look at the odds for passive smokers that do have lung cancer, and that's 120 divided by 11. So that would be this these first two numbers, 120 divided by 11. That would give us the odds for smokers, and that's more than 50%. So their odds are a little bit above 1. And then we would divide naturally if we're looking at passive smokers who do have lung cancer. That might might lead naturally to see, well, what would it be for those that don't have cancer? So you want to see what that comparison or that ratio might look like. So we would add in 80 for passive smokers that don't have lung cancer and divide that by 155, and that would be non-passive smokers that don't have lung cancer. And so that comes out to 2.1. So in other words, someone that's exposed to secondhand smoke actually does have odds that are twice that of those who are not exposed to not exposed to secondhand smoke. So we're beginning to see that there could be a link between lung cancer and smoking. So we've talked about odds ratios, and one way to test that is to use distribution tests for binary outcomes. Those could be 0 or 1, yes or no. We naturally want to know if an odds ratio indicates a significant difference. In other words, it's not happening by chance between groups. The mantle Ansel or binomial proportion tests work. Those are good options. The chi-square test is another option that uses the values from our 2x2 contingency table. It is for binary outcomes with 2 or more exposures or factor levels. All 3 tests use the chi-square test statistic. For example, in the table below, there is a significantly higher readmission for pneumonia cases. We get a chi-square value and the p-value that is associated with that. So that would indicate a very low chance of us being wrong in stating that there is a difference there. And you can click this link to learn more about statistical significance from the course video. And we may want to ask, why do we use logistic regression? We have distribution tests that allow us to do this. We can hand calculate odds ratios ourselves. But the chi-square distribution test is limited in that it only tests associations between 2 categorical variables. For example, we can't assess the difference between readmissions and sex and age. So we can only look at the association between 2 variables, but we can't add a third one in. Logistic regression allows us to control for multiple variables, not just age. We can add in diagnosis and many other predictors. We may ask, can we use multiple linear regression instead? We can't, because it can give us values that don't make sense when our overall outcome rate is close to 0 or 1. For example, it might predict negative 0.1 readmissions for some groups or patients that are 65 and older. They could have 1.31 readmissions when at most they can have 1 readmission. So readmissions is coded as 0 or 1, and we don't go outside that range. We can't do a linear regression directly on probability because it could give us values that don't make sense. And this slide restates what we covered in the previous slide. It shows you the limitations of, it discusses limitations of our distribution tests. For example, if we want to look at more than one predictor, then we need to use logistic regression. And we have common binary or 2-level outcomes such as death, readmission, infection, heart disease, cancer, or a missed appointment, and many more. Logistic regression is a probability model, and what we mean by that is that on the left side of a formula that we commonly might see, such as the probability of a hospital readmission equals age plus sex plus primary diagnosis. Because of the limitations we just covered, that with the binary outcome we're constrained to a value of 0 or 1, and because a multiple linear regression can't handle that, we need to use a logistic regression that does calculate probabilities for us. And so that's why we say logistic regression is a probability model. Everything on the right side of the of this last equal sign are the predictor or independent variables. So if you've used multiple linear regression before, that right hand side looks identical to what you've used in the past. It's just this left hand side which we would need to convert our probability to a logit, and a logit can be converted from a natural log of the probability over 1 minus the probability, or in other words, the odds. So if we get the natural log on odds, that gives us our logit. And when we do that, we can actually use our what we're already familiar with through multiple linear regression. We can use this additive model to get a predicted probability. Um, and because of the mathematical correspondence of logits, odds ratios, and probabilities, we get three types of results. What do we do? What do we get from logistic regression? In terms of our output, we get logits, odds ratios, and probabilities. Logits are natural logs. They allow us to have a linear additive model similar to multiple linear regression. For example, we can multiply the weighted regression coefficient by patient variable values and add them together to figure out a patient's risk of death based on age, sex, and primary diagnosis, for example. We also get odds ratios. We can exponentiate our log odds values to let us know that the odds in favor of death are 2 times higher for men than women. These are most helpful in explaining the results of each predictor. We get probabilities that we can sum our risk and determine that men have a 20% risk of admission. These are most helpful in summarizing total risk. And just to emphasize it, we can say that logistic regression gives us odds ratios. And these are the formulas. And this slide emphasizes that odds ratios can be calculated from exponentiated logits. And so that's the E with B sub J. And we do have a relationship between logistic regression and 2x2 contingency tables. And this slide emphasizes the relationship between odds ratios, probabilities, and exponentiated logits. We can't use probability as an outcome in linear regression, so we use logistic regression instead. A model of the following form might be considered. So we might think about using that 0-1 outcome in a multiple linear regression, but we have issues with that, and so instead we need a logit transformation defined as this. So this is that left-hand side of the formula. And here's what we mean by when we say that that there's a relationship between logits and probabilities. The green line represents logits that are properly constrained within 0 and 1. And that 0 and 1 you see on the left-hand side on the y-axis. They have the blue square around it. And so this is the limit to our of our outcome. It's 0 or 1. And so we can see with these green lines that represent logits that are properly constrained within 0 and 1, we can see as we see a trend get closer to 0 or 1, we see that these extreme values on both ends get pulled in. So this is what we'd like to see happen, is that as we get closer to our values that may give us probabilities of 0 or 1, that they get pulled in closer to those limits. But what we don't want to see happen is what we see with this red line. The red line represents values that are not constrained and they can exceed the true limits of 0 and 1 in multiple linear regression. So if we used a multiple linear regression, what we would see is this red line that actually goes below a 0 or above a 1. Logistic regression allows us to get linear trends that stay within probabilities of 0 to 1, such as that green line. Using logit transformation solves the dilemma of getting credible estimated values from regressions. So in other words, we're not going to get predicted values below 0 or above 1 because that logit transformation we're doing allows us to keep values within that limit of 0 and 1. And so we do have some regression assumptions in logistic regression. Unlike multiple linear regression assumptions, logistic regression assumptions of linearity and additivity are verifiable. Logits provide linearity, and the additivity assumption can be relaxed by using interactions when appropriate. So we only have two assumptions But by using logits, we fulfill that assumption, and we do have a linearity between our in our terms, but we can use interactions when we expect a trend to be nonlinear. So how logistic models improve our analysis: comparisons of predicted trends on binary outcomes for linear and logistic regression. So here's what happens when I just did a simple analysis using the MT cars data. It gave us a value below 0. So 0.0, or a manual transmission, is the lowest value possible. Above that we can't see is a value of 1 for an automatic transmission. So it only is going to range between 0 and 1. We can't have we don't have a value below a manual transmission. So multiple linear regression produces impossible predictions of negative 0.5. Linear regression is designed to work on outcomes beyond the range of 0 to 1. There's an infinite number of values that in the outcome that a multiple linear regression can use, but it can't stay within 0 and 1. In other words, the lowest logit on the right side, we have logistic regression. We have a very similar looking trend. It's a straight line, and we can see on the lowest value of negative 40 for the logit, we can convert that into probability slightly above 0.0. So logistic regression produces sensible values even in the most extreme. We can do partial prediction plots of the outcome predicted by age for the log. We get logits and probabilities. So in logistic regression, we do get log odds, which are linear. So logits range from negative infinity to positive infinity, so the trend line can be flat. Logits lets us think of linear trends between predictors and outcomes needed for regression. And this is the basis for a regression model, is that we add the effects together, such as age, gender, and primary diagnosis. So this lets us be able to do that without giving us values that go beyond the limits of 0 and 1. This is what the logit values look like. And on the right side, because logits, odds ratio, and probabilities are related, we can actually also get probabilities as well. So even though there is an issue of using probabilities for multiple linear regression, it's not an issue for logistic regression. So we see that on the left side we have that straight line that shows us the trend. On the right side we see that this trend, with the predictor and the outcome, actually bends. So this line properly bends, and we have a probability that has a mean of 0 and a max of 1, which is above, which we don't see in this plot. But we can see the trend line, and we can see that as it gets closer to 0 or 1, it's going to start to bend in a way that makes sense, and we get these probabilities on the right side that shows us each of these different values for 0, 1, 2, 3 on the x-axis, and we can see what the expected probability is for each of these. And these are formulas that convert values between logits, natural logs, odds ratio, and probabilities. And this is just to show that these are all related in some way, that we can back transform one value to the other. We don't need to convert these numbers, but it is helpful to know that the different types of calculations and how they are related. What we most often use in regression results would probably be the odds ratio. And so that would just say that what are my chances compared to another category or factor level. So general rules on logits, odds ratios, and probabilities and independent variables. Logits with values greater than 0 indicate an increased chance of the outcome. Values below 0 indicate a decreased chance. And 0 equals no difference or a flat trend. For odds ratios, the values we want to keep in mind are that for values that are greater than 1, those indicate an increased chance of the outcome. Values below 1 indicate a decreased chance. And a value equal to 1 indicates no difference or a flat trend. For probabilities, predicted probabilities above or below the mean suggest an above or below average risk. We have 95% confidence intervals that determine if the above values are significant. And you can click that link on the right side to learn more about confidence intervals. I have some slides ahead that I can explain it more. And so in our first example, we're going to look at hypothesis testing in logistic regression. We're looking at the Dahl and Hill study on lung cancer and smoking. In 1950, Dahl and Hill published a study on smoking and lung cancer. Other studies during the same period showed links between smoking and lung cancer. Dahl and Hill considered the competing cause of auto pollution as well as better lung cancer diagnosis for the increase in cancer cases that they saw. Their chi-square tests and balanced study design showed powerful evidence of the link between smoking and lung cancer. We'll apply simple and multiple linear regression to their main table 4 to test the hypothesis of no difference in lung cancer between smokers and non-smokers. That null hypothesis is smokers' chances equal non-smokers' chances. Here's some information about the patients. Patients from 20 London hospitals were asked to participate in the study after being admitted for lung cancer or non-cancerous diseases. Patients were balanced on age and sex for 709 cases with lung cancer and 709 cases without. Logistic regression lets us balance mathematically when we can't balance in our sample. It was really nice that they're able to balance all of this information when they did their study, but oftentimes, especially in healthcare, we can't balance it just like this. And so what we do see is a higher rate of lung cancer smokers. We see that 99.7% of males and 68.3% of females with lung cancer were smokers. We see that these two circled lines are these two values circled in red. Female non-smokers appear to have other sources of lung cancer, for example, professions, secondhand smoke, or passive smoking, which wasn't asked about in their spouses' habits weren't asked about in this study. So I can imagine when they saw that there were more female non-smokers than male smokers, that must have seemed odd to them. But overall, we see more from both men and women. We see more smokers that have lung cancer than not. The odds ratio of smokers having lung cancer is 688, which is 647 plus 41, divided by 650, which would be 622 plus 28. And then we divide that by 21, which would be, in this table, the 19 females with lung cancer plus the 2 males with lung cancer that didn't smoke. So that 21 divided by 59 it gives us an odds ratio of 2.97. And that's what we saw when we, if we were just to hand calculate the odds ratio, which we did here, that's 2.97. And the results we get from a binomial test, this is the other option we could have gone with, and this is what the authors did. They did a binomial proportion test, or I think they did a chi-square. They both come out to the same results, and they both use a chi-square distribution to give you that significance value. We might begin with the distribution test. Smokers have a higher rate of lung cancer than non-smokers, and we can hand calculate that and see that in this result. Or we can also use logistic regression. Below is the output from a simple logistic regression. That means one predictor. The tabled results in the top half have the natural log of odds, and we see that's highlighted in that red box. It's 1.0898. And so since we're working with logits and we know that the value is above 0, that means it increases the odds, and it's in the bottom half has the exponentiated odds ratio. So if we were to exponentiate that 1.0898 to give us an odds ratio, that would give us 2.97, which equals the same value that we get when we hand calculate our odds ratios. And in this data, we see that we have an intercept, and so that's kind of our baseline. That would be the baseline for non-smokers. We can convert that value to a probability of 0.26. So we have on top, we have our values of our logits. We have p-values, so we know that difference that we have between smokers and non-smokers is very significant. And you can click this link on the bottom right side to learn more about statistical significance. And on the bottom, we have our exponentiated coefficients to give us what we call odds ratios. So we know smokers are about 3 times more likely to get lung cancer than non-smokers. So with logistic regression, we can add in a second predictor. We want to control for differences between men and women. We can't add a second predictor into a chi-square test, so we use logistic regression. Our conceptual model is that lung cancer equals smoking plus male status. The logistic regression model is seen below. On the left side of the equal sign, we see the log odds. This symbol alpha, the Greek letter alpha, which looks like an A, represents our intercept, which is the baseline in all models. And the beta E, or the BE, represents our predictor values. And so before we go further, I just want to share this slide because it gives us an idea of how many predictors we can have in a model. We're starting out with 1 and 2 predictors, but we may want to know how many can we have. For example, in our lung cancer data set, we have n equals 709. We have 709 with cancer, 709 without. And so from this section from Frank Carroll's book, he recommends using m divided by 10 or m divided by 20, and m represents is the limiting sample size, and that's limited by the number of zeros or 1 you have, and it would use the lower of the two. So in this data set, they're balanced, so the number of zeros equals the number of ones. But maybe in some data sets we might have 40% have a 0 and 40% or 60% have a 1, or maybe it's vice versa. In that case, if we had 100 patients in our data set, we would use whatever group made up 40%. So that would be 40 divided by 10 or 20. Harold actually recommends using, for your denominator, using 15, which is, he said, just because it's in between 10 and 20. So if you have 40, if your lowest group has 40 in it, say it's the group that had a 0, then we would divide 40 by 10 or 40 by 20. That would give us either 2 or 4 predictors that we can use. So that would give us a good way of knowing about how many predictors we can have in a model that won't be too dangerous to our interpretation. Sometimes we can overfit, and we want to avoid that, where we get. So we want to have results that are going to hold up in the future. So this is knowing how many predictors we can use allows us to better do that. So here are the results from a multiple logistic regression model. The results show that being a male is associated with a lower risk of lung cancer. It is important to note that the researchers didn't take into account if females were passive smokers. For example, in other words, females may have been exposed to secondhand smoke. Highlighted in with that red box, we have standard errors, and those help us define a normal range. And the inverse would be the significant values. So everything that's within, say, 2 standard errors would represent that normal range, and everything with that's outside of that of 2 standard errors, such as 2 times 0.2652, that's when we start to see significant differences. The area under the curve on the right side, we can see the area under the curve, or concordance statistic lets us assess our model performance. 0.54, which we see on the top right, is too low to be adequate for individual predictions, but it is sufficient to test a hypothesis, such as, is there a link between smoking and lung cancer? We'll cover more of that later. So this is how we can interpret coefficient results from logits. For the smoker, say that logit in the middle in that box, that red box, it's about 1.45. Because the logit is above 0, we know there is a greater chance of lung cancer for smokers than non-smokers while controlling for male gender. For male, it is negative 0.05, or it's negative 0.58. The logit is a negative value, which indicates that men may have a lower risk of lung cancer when controlling for smoking status. And the intercept is negative 0.84. This indicates that the baseline risk and is the value for female non-smokers. This low coefficient indicates that these patients have a generally low but not the lowest risk. Because smoker and coefficients indicated change in the outcome due to a 1 unit increase in the predictor. Here, smoker and male only range from 0 to 1. Because smoker and male status are coded as 0 for not present or 1 for present, it represents a change in logits for lung cancer. Here, being a smoker increases logits, while being male decreases logits. And this is how we can interpret coefficient results from odds ratios. And it's important to note that these are positive values. Smokers, that odds ratio is 4.25, because the odds, and this is what we see on the bottom left side, towards the bottom in this gray output of exponentiated coefficients, our smoker value is 4.25. Because the odds ratio is above 1, we know there is a greater chance of lung cancer for smokers than non-smokers while controlling for male gender. The odds in favor of lung cancer are 4.25 times higher for smokers than non-smokers while controlling for gender. To understand the male effect, which is 0.56, the odds ratio is less than 1, which indicates that men may have a lower risk of lung cancer when controlling for smoking status. The odds in favor of lung cancer are 0.56 times, or 44% lower for smokers and non-smokers while controlling for smoking. The intercept is 0.43, although not technically an odds ratio, we can still calculate the odds are 0.43 times, or 50% lower for female non-smokers. The formal interpretation of a single predictor includes how we control for the independent variables in the model. For example, it's the part of the sentence that is while controlling for smoking. However, it is okay to describe your results by only mentioning the single variable, since it is implied that we control for the other variables in a regression. And here's how we can interpret statistical significance of the coefficients p-values. For the smoker, it's less than 0.001 from the p-value column on the right, and we see that in that red box on the right side. We know that this is a significant difference. In other words, we know there is less than a 5% chance. We use an alpha of 0.05 of being wrong and stating there is a significantly higher chance of lung cancer for smokers. The male effect for that, the p-value, it's 0.014. This is significant at the p is less than 0.05 level. P equals the probability of a type 1 error of stating something is significant when it is not. And for the intercept, that p-value is 0.0015. This is almost always significant because we are just trying to measure the baseline. In bigger models, the intercept doesn't always represent all predictors equal 0. And that's what that baseline should represent. For this, on the right side, bottom right side, we can see that we have standard errors let us determine a normal range. So you'll notice that there's other columns such as COEF for coefficient, SE for standard error, Wald Z is the Wald Z statistic, and that probability, that p-values that we just discussed. We get that by dividing our coefficient by our standard error, which gives us the Z statistic value. And if Z exceeds the critical value, we have a significant result. So the further away from 0 that Wald Z statistic is, the more significant our outcome is. And so you see that 4.77 is less than 0.001. So that means there's greater significance in that result. And click on the bottom left-hand side, click this link to learn more about statistical significance. And here's how we can interpret model performance. There are various methods to assess model performance. The most common method of assessing performance is through the area under the curve, which is also referred to as a concordance or C statistic. And this is on this gray output at the bottom. It's on the right-hand side. Values range from, for the AUC, values range from 0.5 to 1. Values greater than 0.7 are considered good, but lower values may make models still useful. For example, the C statistic of 5.35 is too low for individual predictions, but are still valid for hypothesis testing. And on the left side, we have the likelihood ratio test, which indicates if the model has some predictive power greater than chance. R squared is the amount of variance explained. It's less useful in logistic regression because of binary outcomes. It's more useful in multiple linear regression because because we use continuous outcomes. These are rules of thumb on AUC and C statistic values for predictive modeling. Helpful to consider how well can we predict an outcome. So ideally, we whatever we try to predict, we're going to do a great job on it. But some things are just a lot harder to predict than others, such as it's probably a lot easier to predict lung cancer than hospital readmissions because we have such a strong link between smoking and lung cancer. We don't really have something like that with readmissions. So just for our rules of thumb on our AUC, a value of 0.5 is equal to a random guess. AUC ranges from 0.5 to 1, and if we do get something that's 0.5, that's odds are we coded our outcome backwards. Values between 0.5 and 0.6 indicate a poor value. Hypothesis test results are still valid. It just doesn't explain it all. There's other things out there that we're missing. For example, with the lung cancer one, we probably were. It probably would have helped if we had information about females' passive smoking. For AUC values between 0.6 and 0.7, that represents a moderate fit. Models still useful. Some outcomes are tough. So readmissions, for example, we use readmissions models that are in that range. If we get an AUC between 0.7 and 0.8, that represents a good fit. We can begin to reliably predict individual outcomes. 0.8 to 0.9, that's very good. And at 0.9 or above, that represents an excellent fit. However, we should be aware of results that are too high. We may want to ask ourselves if there is overfitting. Are we just predicting something that's going to work well on our data now, but not carry over into the future? Lower AUC values that aren't ideal for individual predictions can work well for groups. For example, the widely used Framingham heart disease model has an area under the curve of about 0.65. Some outcomes are difficult to predict, so we use the best available option. We can still reliably use it for gender groups, disease groups, or other types of groups. And we can calculate predictions from model output. We want to get predicted probabilities. Your software will produce the predictions for you, but here's how it works. We multiply the coefficients by the patient values and sum the logits. Patient values are in red. We can do it by adding logits, such as the values that we get for the intercept plus smoker plus male. For example, for the female non-smoker, we would use that intercept value of negative 0.8421, and we would add that to the coefficient value of 1.4481 times the value of smoker. Because it's a female non-smoker, that smoker value is 0. So 1.4481 times 0 equals 0. Then we would add that running sum to with negative 0.5781 times 0 for male. Again, this person is a female non-smoker, so that value of male is coded as 0 or 1. Since this person's female, their value is 0. We sum that, and that comes out to negative 0.84. And we can convert that into a probability of 0.30. And so we do the same for female smokers, male non-smokers, and male smokers. For example, that intercept of 0.841 is added to the smoker effect on the Logit scale of 1.4481 times 1. It's a male, so that value is 1. Then we add it to negative 0.5781 times 1, and that 1 is because this patient is a male. And then we sum that together, we get a Logit value of 0.028, and then we can convert that into a probability of 0.51. And the next slide will show us how to get the probability values in green above. So this is how we use exponentiated log odds to get probabilities. We calculate odds ratios and then convert those into probabilities. So we see that we're calculating probabilities from predicted logits. And so this is just that process that we go through. This male smoker value, for example, it's 1.03 divided by 1 plus 1.03, and that's the formula that we use to get our probability of 0.51. Surprisingly, female smokers, few in 1950, had the highest risk at 0.65. But it may be impacted by being exposed to secondhand smoke by spouses. Both male and female smokers have above average risk. They're above 0.50. The lung cancer rate in the sample is 0.50. If it was 0.60, then they would be below average if those probabilities were identical. And we can calculate contrast from predicted values. We can calculate differences in predicted values, P1 minus P2, Alternatively, we can do contrast in the RMS package that tests if the difference is significant. For example, below we see the contrast between male smokers and female non-smokers. The contrast is a logit of 0.87 and the p-value is 0.0015. Therefore, we know the difference is significant. So here's our contrast. We can get a predicted value for each of the groups, but doing a contrast gives us a standard error, which allows us to see if it's within that normal range or if it's in a significant range, such as we see with this probability at 0.0015. And here are some examples of the commands in R and SAS. On the top we have the standard R command. Below that we have the RMS package for R. LRM is the equivalent to GLM for logistic models, and then in the bottom part we have our SAS command. And here's some ways of how we can visualize our odds ratio. We can do graphs, and just to reemphasize, effects above 1 indicate an increase in the outcome, effects below 1 indicated decrease in the outcome. We see effects above 1 for smoking status and effects below 1 for male status. Effects are significant when the blue confidence bar excludes 1. The blue bars are 90, 95, and 99% confidence intervals. The very blue shaded more narrow bar represents the 90% confidence interval. The medium shaded blue represents that 95% confidence interval, and that's the one we almost always use, but this display gives us the option all three. If you want to be very, very confident, if this vertical gray line excludes that very light blue or the whiter blue line, that's a 99% confidence interval. So we would have maybe more certainty that these are very different than by chance. These graphs make it easy to show that smoking greatly increases the odds of lung cancer. The blue bars of the 95% confidence intervals show that the normal range goes from around 2.5 to 7.5. In other words, in 95% of different samples, we are likely to see the odds ratios within that range. And another graph we can look at is called a variable importance plot. The p-values on the far right are from the output, and it's on the right hand side. The values to the left are the chi-square. Roughly the more important predictors have the higher chi-square. Not always, because maybe some have many categories, but usually it's similar to what you would see in your output. The most important predictors of your outcome have dots furthest to the right, so these give you the biggest bang for the buck if you can focus on that. For this analysis, we see that the smoker effect has a dot very far to the right, so that would mean that that one is much more important than the male status. And for this graph, we're looking at partial prediction plots. This graphs the effect of each predictor while controlling for the other predictor. What we can say is the effect size while holding other predictors constant or controlling for other predictors means we use the average for each predictor to calculate other predictor effects. For example, the partial prediction of lung cancer for male equals 1, and 0 uses the same predictor values in the formula. Here we hold smoker constant at 0 and use different values for male. So in that formula it uses those logits of negative 0.84 plus 1.45, which is the effect size, times smoker equals 0. So that part remains constant. The only thing that we change would be that effect of negative 0.59 times the male status, the male variable value equal to 0, or the male variable value equal to 1. And so when we do that, we see that we get two different outcomes, negative 0.84 or negative 0.143. If there are more levels to male, or if we used a variable that had a high, medium, or low, that the first half of values would remain constant, and we would just modify that male equals value. And we would do the opposite for smoker. In that case, male would equal a constant value, either 0 or 1. And say if we hold it at 0, then that smoker value would, in the calculation, smoker would equal 0. And then that next row, smoker equals 1. So that's what we mean by we're controlling for a variable or holding it constant. This is just how it's just represents that formula. And we can do the same type of partial prediction plots, but using probabilities, which might be easier for people to look at. Some may prefer odds ratios, but maybe some would prefer looking at probabilities. And that's on the y-axis on the left side. We can see that in this graph we have probabilities of 0.2, 0.4, and 0.6. In summary, Dahl and Hill's Table 4 shows a link between smoking and lung cancer. The study design was carefully created and assessed. The authors clearly explained concerns of bias in sampling, and results show a strong link between smoking and increased rates of lung cancer after ruling out other influences. And this is their summary of the results. And in this example, we can see that we can use aggregated data in logistic regression. We maybe are working with dashboards or scorecards. We only get a few rows of data. In this example, we're looking at eight rows of data, and this is to predict hypertension. And here's the formula. And so this is the actual data, and our logistic regression model is on those 8 aggregated rows of data. We can do logistic regression on proportion by adding in the variable n.tot, which is the number of total rows, as a weight option. For example, 60 rows have no as responses for the 3 variables in that first row. And then we get results similar to what we just looked at with the lung cancer example. And weighted regression can be used to perform the same type of analyses and give us the same types of graphs. And you can click this link on the top left if you want to learn more about weighted regression. And we can see that we can get these different types of results as well. Okay, so that is it for this session. We'll cover more in session 2. Thank you.